Dear Sir, Madam, and everyone, I am Ngọc Nguyễn, an independent scholar from Vietnam. Today, I am very honored and happy to present my research, a general framework of particle swarm. My research was presented in the PIT Bihabbo University, the School of Advanced Science and Language, SAS, in the international workshop in March 2021. Particle swarm optimization (PSO) is an effective algorithm to solve the optimization problem in case that the derivative of target function is inexistent or difficult to determine. Because PSO has many parameters and variants, I propose a general framework of PSO called GPSO with aggregates important parameters and generalized important variants so that researcher can customize PSO easily. Moreover, two main properties of PSO are exploration and exploitation. The exploration property aims to avoid premature converging so as to reach the global optimal solution, whereas the exploitation property aims to motivate BSO to converge as fast as possible. The two aspects are equally important, for CBSO also aims to balance the exploration and exploitation. It is expected that GPSO supports user to thin parameter for not only solving premature problem, but also fast conversions. This is the table contains 1. Introduction, 2. GPSO with probabilistic constriction, 3. Experimental result, 4. Conclusion. Introduction. Particle swarm optimization (PSO) algorithm were developed by James Kennedy and Russell C. Eberhard. The main idea of PSO is based on social intelligence when it stimulates how a flock of birds search for food. Given a target function known as a cost function or fitness function (fs), the optimization problem is to find out the minimum bond S star, known as a minimizer or optimizer, so that Fs star is minimal. Traditional optimization methods such as Newton-Raphson and Radian 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 descent require that Fs is differentiable. Alternately, BSO does not require existence or differential. BSO scatter a population of candidate optimizer for a star, and such population is called swarm, where its candidate optimizer is called particle. BSO is iterative algorithm running over many iterations in which every particle is moved at each iteration so that it approaches the global optimizer S star. The movement of each particle is affected by its path position and the path position of the swarm. This is the description of BSO. Input: the swarm S of particles along with their initialized position and velocities. Output: the global path position Bg of anti-swarm so that Bg is equal or approximated to the global minimizer SR. Initializer, let L and U be the lower bound and upper bound of particles on current position Si of all particles are initialized randomly. Moreover, their best positions Bi are said to be their current position, such that Bi equal Si. Initialized on current velocities Vi of all particles are initialized randomly in the range from negative U minus L to positive U minus L. Vi, Vi1, Vi2, Vi1, where Vij belong to the interval negative U minus L, positive U minus L. Initializer Bg is the best among local best position. Bg equal argument mean of Fbi over Bi. The main loop of GPSO is shown in the next slide. Why terminated condition is not met do. For each particle I in swarm S, velocity of particle is updated according to following equation 1 bond 1. Position of particle I is updated according to following equation 1 bond 2. Si equal Si SVI. If Fsi smaller than Fbi, then the best position of particle I is updated Bi equal Si. If Fbi smaller than Fbg, then the best position of swarm is updated Bg equal Bi, and if and for Ny. Introduction. Equation 1.1 is the heart of GPSO, which is velocity update rule. Equation 1.2 is position update rule. Two most popular terminated conditions are that the cost function SPG, which is evaluated as FPG, is small enough, or BSO grand over a large enough number of iterations. Function U 0v1 and U 0v2 generate random vector whose elements are random numbers in range 0v1 and 0v2 respectively. The operator circle cross denotes component-wise multiplication of two bonds. The two components U 0v1 circle cross Bi subtract Si and U 0v2 circle cross Bg minus Si are attraction forces that push every particle to move. Sources of force U 0v1 circle cross Bi minus Si and force U 0v2 circle cross Bg minus Si are the particle I itself and its neighbors. Parameter V1 along with the first force expressed the exploitation, where a parameter V2 along with the second force expressed the acceleration. The larger V1 is, the faster BSO converges, but it tends to converge at local minimizer. In opposite, if phi2 is larger, convergence to local minimizer will be avoided in order to achieve better the global optimizer. But the conversion speed is decreased. They are called acceleration coefficient. Velocity vi can be bounded in the range negative Vmax and positive Vmax in order to avoid out of conversion trajectories. Because any movement hay initial 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 force is added to the two attraction forces, which is represented by a so-called initial weight omega, where omega larger than zero and smaller or equal 1 according to equation 1.3. The larger initial weight omega is, the faster particles move, which need BSO to explore the global optimizer. The smaller omega needs BSO to explore local optimizer. In general, large omega expresses exploration and small omega expresses exploitation. The popular value of omega is 0.7298 given V1 equal V2 equal 1.4962. If velocities Vi of particles are not restricted, their movement can be out of conversion trajectory at acceptable levels. Thus, a so-called constriction coefficient chi is robust to thermodynamics of particles. According to equation 1.4, Vi chi Vi at U0 V1 circle Bi minus Si plus user 0 V2 circle Bg subtract Si. Equation 1.3 is the special case of equation 1.4 here, when the expression chi Vi is equivalent to the expression omega Vi. Initial weight omega also damn dynamic of particles. This is the reason that omega equal 1 when chi different from 1, but chi is stronger than omega because the chi affects reverse velocity and to attraction forces, whereas omega affects only reverse velocity. Popular value of chi is 0.7298 given V1 equal V2 equal 2.05 and omega equal 1. Introduction. Structure of swarm, which is determined by the finding neighbors and neighborhood of every particle, is called swarm topology. Because BZ is the best position of anti-swarm, the attraction force U 0v2 circle BZ subtract SI indicate the movement of particle is affected by all other particles, which means that every particle connects to all remaining particles. Alternately, swarm topology can be defined in different ways so that each particle I only connects with a limit number ki of other particles. So, each particle has only ki neighbor. According to equation 1.5, where Qk is the best position of k neighbor of particle I. Qk equal Bj such that particle J is the kth neighbor of particle I. Equation 115 indicates a mandate fully informed particle swarm FIPS method, which specifies the local best topology, where a reverse equation 111, 112, and 114 specify the global best topology Z. The global best topology in the global best topology specified by equation 111, 113, and 114. Only one best position Bz of anti-swarm is captured in local best topology specified by equation 115. Many best positions from groups implied by neighbors are captured. Hence, FIPS converge slowly but avoid converging at local optimizer. In other words, local best topology aim to exploration rather than exploitation. However, at compromise, FIPS makes convergence speed of PSO slow because the exploitation is scarified for the exploration. Therefore, I propose a general framework of PSO in next session, which aims to balance the exploration and exploitation. Therefore, I propose a general framework of PSO in next session, which aims to balance the exploration and the exploitation. GPSO with probabilistic constriction. The two main aspects of PSO are exploration and exploitation. The exploration aspect aims to avoid premature converging so as to reach the global optimizer, whereas the exploitation aspect aims to motivate PSO to converge as fast as possible. Besides, exploitation property can help PSO to converge more accurately regardless of local optimizer or the global optimizer. These two aspects are equally important. Consequently, the two problems corresponding to the exploration and exploitation are premature problem and dynamic problem. Solutions of premature problem are to improve the exploration, and solutions of dynamic problem are to improve the exploitation. Inertial weight and constriction coefficient are common solutions for dynamic problem. Solutions of premature problem relate to increase dynamic ability of particles set A. Dynamic topology, chain of finite function, adaptation includes thinning coefficient, adding particles, removing particles, and, and changing particle gravity. Diversity control. GPSO with probabilistic constriction. The global general framework of PSO called GPSO is the abbreviation of general of PSO to balance the exploration and the exploitation, which solve the premature problem and dynamic problem. If we focus on the fact that the attraction force exerted by a particle I itself is equivalent to the attraction force from the global best position BZ, and the other attraction function from its neighbor QK. Equation 115 is modified as follows according to following equation 211. In equation 211, the set of Ki neighbors does not include particle I, and so the three parameters phi1, phi2, and phi are coexistent. In this inertial way, omega is kept intact too. Thus, GPSO with balanced local best topology and the global best topology so that conversion speed is improved, but conversion to local optimizer can be avoided. In GPSO specified by equation 211, it is possible to relocate neighbors of a given particle at each iteration. Therefore, dynamic topology can be achieved by GPSO, which depends on individual application. In BSO theory, solutions of dynamic problem are to improve the exploitation so that BSO can converge as fast as possible in this inertial way, and constriction coefficient are common solutions for dynamic problem. Hence, constriction coefficient is thin with GPSO. However, thinning a parameter does not mean that such parameter is modified simply at each iteration, because the modification must be solid and based on valuable knowledge. Fortunately, Kennedy and Eberhard wrote both Barebone BSO, BBSO, in which they asserted that given SI1, SI2, SIN, PI, BI1, BI2, BIN, BZ, BZ1, BZ2, BZN. The J11 SIZ of SI follows normal distribution, which means BIZ at BZJ, BIJ at BZJ divided by 2, and the variance Bij subtract BZJ power 2. Based on this valuable based on based on this valuable knowledge, I think constriction parameter carry with normal distribution at its iteration. Based on this valuable knowledge, I think constriction parameter carry with normal distribution at its iteration. Let GI, GI1, GI2, GIN be random vector corresponding to its position at I of particle I. Every J enabled Gij of Gi is randomized according to normal distribution, which means Bij at Bgj divided by 2, Bij subtract Bgj power 2. Let Gij be the pseudo probability density function of Gij according to equation 213. Let uppercase K, K1, K2, Kn be probabilistic constriction coefficient according to equation 214. The K is replaced by probabilistic constriction coefficient uppercase chi, so that equation 2.5 is the most general form of GPSO. Please pay attention that equation 2.5 is the main equation of GPSO. According to equation 2.5, with probabilistic constriction coefficient chi, the closer to the global best position BZ, the local best position BI is, the more dynamic the position SIE, with M to exploration for converging to the global optimizer. The farther to the global best position BZ, the local best position BI is, the less dynamic the position BI is, which aims to exploitation for fast convergence. This is purpose of adding probabilistic constriction coefficient uppercase chi to equation 2.1 for solving dynamic problem. A convention GPSO specified by equation 2.5 is called probabilistic GPSO. The shortcut of GPSO and probabilistic GPSO is available at following link. Experimental result. GPSO specified by equation 2.1 and probabilistic GPSO specified by equation 2.5 are connected with the basic BSO specified by equation 1.4. The cost function, finite function, is specified by equation 3.1. The lower bound and upper bound of position in initialization stage are L -10, -10, and U 10, 10. The terminated condition is that the bias of current global best values and reverse global best value is less than epsilon equal 0.01. Parameter of GPSO are phi1 equal phi2 equal phi equal 2.05, omega equal 1, and chi equal 0.7298. Parameters of probabilistic GPSO are phi1 equal phi2 equal phi equal 2.05. Parameter of basic BSO are phi1 equal phi2 equal 2.05 and chi equal 0.7298. The swarm size is 50. Dynamic topology is established at each iteration by a so-called finite distance ratio (FDR). Given target particle and another particle, given target particle I and another given target particle I and another particle J, their FDR is the ratio of difference between FSI and FSJ to the Euclidean difference between Si and Sg. If FDR Si is larger than a threshold, larger than 1, the particle J is a neighbor of the target particle according to following equation. Experimental result. The two best value of target function specified by equation 3.1 is negative negative 1, and it's true the global optimizer is S star 3.1416 3.1416 from the experiment basic BSO, GPSO, and probabilistic GPSO converge to the best value to the best value minus 0.9842 minus 0.9973 and minus 0.9999 with the global best position 3.0421 3.1151 3.1837 3.1352 and 3.1464 3.1485 after 6, 18 and 18 iteration respectively. Finite bias and optimizer bias of probabilistic BSO are smallest. Therefore, probabilistic BSO is the remedial one. Basic BSO converges soonest after 6 iteration, but basic BSO cope with the premature problem due to no its converge finite value, whereas the GPSO and probabilistic GPSO solve the premature problem with better converge finite value, negative 0.9973 and negative 0.9999, but they require more iteration, 18. The reason that GPSO is better than basic BSO is the combination of local best topology and the global best topology in GPSO. The event that probabilistic GPSO is better than GPSO prove that the probabilistic constriction coefficient can solve the dynamic problem. The event that probabilistic GPSO is better than GPSO prove that the probabilistic constriction coefficient can solve the dynamic problem. The experimental result shown in the table. Conclusion. The first purpose of GPSO is to aggregate important parameters and to generalize important variants is connected with the general form of velocity update rule. But the second purpose is to balance the two BSO properties such as exploration and exploitation. A creature at molecular grade onto experimental results show that GPSO and probabilistic GPSO are better than basic BSO due to combination of local best topology and the global best topology, along with definition of probabilistic constriction coefficient, which rule the improvement of the global conversion. The reason of balance at molecular grades is that dynamic topology in GPSO is supported indirectly with general form of velocity Peru, which is impractical because researchers must modify shortcut of GPSO in order to define dynamic topology. Moreover, premature ngầm is shown by many other solutions, such as dynamic topology, chain of finite function, adaptation, thinning coefficient, adding particles, removing particles, removing particles, changing particles properties in diversity control over iteration. In future chain, I will implement dynamic solution as much as possible. Thank you for your attention. I am very honored and happy to answer your question. There are references in the research.